Okay, so welcome to this next video in the Theory of Probability playlist. In this video we're going to discuss the topic of convolution of two random variables. Convolution of two continuous random variables. Those are these. Okay, right, so this is the setup. Let's say we have a random variable here. Sorry, we have an abstract probability space here. I do apologise. We have an abstract probability space here, which is a sample space, a set of events, and a probability measure. And we have two random variables defined on this abstract probability space. So two mappings which are going to map every single outcome in here onto a real number. So this one's going to map you onto x of s, and this one is going to map you onto y of s. And what we now so these are random variables, meaning that these probability spaces, we're going to set them up so that they mirror the structure of this probability space, so that any event in here has a corresponding event back here, and the probability in this probability space of that event is the same as the probability of the corresponding event back here. Okay. So we can create some. These are two continuous random variables, by the way, two continuous random variables. So x and y are continuous random variables. So we can have the probability density function of the random variable big X as a function of little x, which is just some function here which assigns every real number, little x, a value that doesn't necessarily have to be between 0 and 1, but is just any real number, which is the probability density at that point. So you can't say what the probability of that number happening is, but you can say what the probability density of it happening is, which is if you take a tiny little interval at delta x and multiply it by the probability density at x, then that will approximately give you the probability that you're within that little interval there. Okay, so we've got these two probability density functions. We've got one for y as well, which is a function of little y, let's say. And now the idea is we want to create a new random variable. So we want to create the random variable x plus y. So every outcome in here, every outcome s in here, is ascribed a real number by this function x. It's ascribed a real number x of s, and it's also ascribed a real number y of s. So this new function that I'm going to define, x plus y, that is going to map any outcome s onto the real number that x mapped onto, plus the real number that y mapped it onto. So that's a perfectly well-defined function because every outcome has an x value and a y value, so I can add those two together and ascribe it this new value. And again, I'm going to make this probability space mirror the probability space structure on there. So if you take an event in here, it will have a corresponding event back there, and the probability of that event in here is going to be the same as the probability of that event back there. Given that, I want to know what is the probability density function of x plus y, and I'll say as a function of little t. So I want to say, if you give me any little t as a real number, I want to know what's the probability density function that you're going to be that value of t. Well, that's what we're going to calculate. This probability density function is said to be the convolution of the random variable x and y. So that's what convolution is. It's the probability density function of these two random variables combined together in this way that you add them. So the convolution of x and y. Okay, so let's try and work out what this probability density function is then. So a good way to do this is to think of these as being a joint random variable. So they together, they can be thought of as a joint random variable, x and y, which ascribes you to each outcome an ordered pair, x of s, y of s, which is an element of R2 over here. So then what we can do is we can think of having a and of course, well, you can. This is going to work no matter what, but we will have some joint probability density function here on the R2 plane. So you'll have ascribed to R2, you'll have a PDF, a joint PDF. Now, if these two random variables x and y are independent, we know that the the joint probability density function, the probability density function of x and y, is just going to be equal to the probability density function of x evaluated at the little x times the probability density function of big Y evaluated at little y. That is only true if the two are independent, though. That's the definition of independent. For all little x and little y are elements of the real numbers, basically. That needs to hold true. So if they are independent, this will hold true. But in fact, we can calculate the convolution of the two random variables x and y for whether they are independent or not. The thing is that if they're not independent, then we won't know what this joint random variable, joint PDF is. If they are independent, then we know, obviously, if we know these two, we know it's joint PDF instantly. So the formula looks prettier because if they are independent, because we can replace the joint PDF with the marginal PDFs multiplied together. But if we don't have that, we can just leave it as the joint PDF, basically. So this works. You can take the convolution of two random variables, whether or not they're independent. It's just knowing the marginal distributions won't tell you. It's not instantly apparent how to find the joint PDF if you only know the marginals. It's very nice if they're independent. Okay, so. Now we've got this joint PDF defined on R2. So here is our R2, and we have this joint PDF which ascribes to every ordered pair, little x and little y, it ascribes the probability density, i.e. if you're in a tiny little box and you want to know what the probability of that tiny little box is, it's approximately equal to the PDF times the area of that tiny little box. So we want to work out the probability density function of this new random variable x plus y. Basically, it's quite difficult to directly get the PDF, just as when we were doing the Cauchy distribution. If you try and actually get the PDF directly from this joint PDF here, you're bound to make a mistake, a subtle mistake, basically, you'll make somewhere. Whereas it's very easy to find the CDF of this random variable. So that's what we're going to do instead. We're going to find the CDF of x plus y as a function of little t. So remember what that means. That means the probability of the event that x plus y is less than or equal to t happening. Now, what is this event in terms of this picture of R2? Because the idea how we're going to work out the probability of this, how we're going to work out this CDF is basically we're going to say what's this event in R2. We can work out what the probability of that event is using the fact that we know the joint PDF in principle of this joint random variable, and we certainly know it easily if we know the marginals. Okay, right. So what does this event look like? Does the event that x plus y is less than or equal to little t look like? Well, that means that the value that big X ascribes, which is little x, and the value big Y ascribes, which is little y, needs to be less than or equal to t. So, if we draw the curve that corresponds to, let's draw the line firstly. Let's firstly draw the line x plus y is equal to t, which is part of this subset, but of course this subset is huge, whereas this is just a line. Okay, so let's firstly draw this line though, and then decide what this region is. Okay, so x plus y is equal to t. So if x is equal to 0, then that means that y must be equal to t. So if x is equal to 0, y must be equal to t up here. And if y is equal to 0, then x must be equal to t. So we've got 2 points. That uniquely specifies the line. We can now draw the line through there like that. Okay, now what we need to do, of course, in this case, t was a positive value. If t was a negative value, you'd obviously have a line more down there. Okay, right, so now what we need to do is work out what this region corresponds to. So, we need to work out, does the region x plus y is less than or equal to t correspond to the left side, the region to the left of this line, or the region to the right of this line? Well, if you go to the left of this line, then you either lower the x component or you lower the y component. So when you add x plus y together, it's certainly, if you take any number to the left of, if you take any ordered pair to the left of here, you can just go along to its horizontal point down here, and the y value in this case has stayed the same, but the x value has got smaller, so x plus y must now be less than t, since on that line x plus y was equal to t. So basically it's going to be this region to the left. So the event that big X plus big Y is less than or equal to t corresponds to all the points that are to the left of that line. So if we want to know what the probability of that event having happened is, it's going to be the integral, the double integral over that pink region, so over pink, of the probability density function, the joint probability density function evaluated at little x, little y, which if it's independent we can replace with this, if it's not we can't, so we'll just leave it there in full generality now, dx dy. Okay, so now all we need to do is work out the limits of integration. So firstly let's say we integrate y from negative infinity to infinity. So we go along and integrate y all the way down from negative infinity to infinity, and then we're just going to alter the limits of integration for the x one. Okay, and we're integrating this joint PDF evaluated xy dx dy. Okay, so now we need to decide what are the limits of integration for x. So if you take any fixed value of y between negative infinity and infinity, we need to work out what are the limits of integration for x. So we're going to start, whatever value of y you're at, you're going to start. So even if you're up here, you're going to start off at negative infinity. So we integrate from negative infinity, and then we go along all the way until we get to this point here. So the point on this line, basically, and this was the line that x plus y was equal to t. So what's your x value there? Your x value is t minus y. So if you give me your y value, I know how far I need to integrate to. I need to integrate from negative infinity to t minus y, basically. So that's where I get those limits of integration from, basically. So this integral here gives me the it's equal to this CDF here of the random variable x plus y evaluated at little t is equal to the integral from negative infinity to infinity, the integral from negative infinity to t minus y of the joint PDF evaluated at little x, little y, integrated with respect to x, and then integrated with respect to y. Now, we wanted the PDF, however, so we need to differentiate this thing here. Basically, the PDF of big X, the random variable big X plus big Y, evaluated at little t, is going to equal the derivative of this thing. Now, basically, if you change we're differentiating with respect to t firstly. So if you differentiate this with respect to t, what you basically have, this bit in here is a function of t because you've got this limit depending on t, basically. This outer integral is not a function of t, it's integrating a function of t. So obviously you're worried because this is an integral from negative infinity to infinity. That looks a very scary thing in analysis. But without too many conditions, you can interchange the order of the derivative and the integral. We're wearing our applied mathematician's hat, so we won't worry about the technicalities, we'll just do it willy-nilly. Let's interchange the order of the integral and the derivative. So I need some more paper here. So we are trying to find the PDF of this random variable big X plus big Y evaluated at t, and we know that that's equal to the derivative with respect to t of this great big function of t, which is the integral from negative infinity to infinity, the integral from negative infinity to t minus y of the joint PDF of big X big Y evaluated at little x little y dx dy. Okay, right, and I've said, okay, we're going to interchange the order of this first integral and the derivative, because if you think about it, what we're doing is we're adding on a tiny delta t here, we're taking it away from the original thing and then dividing by delta t, so that process interchanges with this integral. What's not trivial is that the limiting process interchanges with that integral, but without too many conditions we can say that will happen. But basically, do a course in real analysis if you're worried about that. Right, so we'll integrate from negative infinity to infinity. We'll then differentiate this inside thing here, which is the integral from negative infinity to t minus y of the probability density function, the joint probability density function of x and y, evaluated at little x, little y, dx, and then outside of that you've got the dy for this outer integral, basically. Okay, now if you differentiate an integral like this, so this is basically the first fundamental theorem of calculus now. If we have an integral, let's say from a to a variable x of a function, let's say f of t dt, and we are differentiating with respect to x. So what that means is, let's say, draw a picture. We have a here, we have some function here defined on, let's say, an interval a to b, and we have some variable x which is within this interval, and we're going to differentiate, and basically what we're doing is we're integrating from a to x, and you can just think of this as the Riemann integral for our purposes. We're integrating from a to x, which will find the area underneath that curve, okay? And then what we're doing is differentiating with respect to x. So we're saying go forward by a tiny amount, delta x, work out the new integral. You'll get something that's converging on 0 as you converge delta x on 0. But if you then take the difference between, basically what you're doing is you're taking the integral from a to x plus delta x of f of t dt minus the integral from a to x of f of t dt. So, and then dividing that by delta x. And then taking the limit as delta x approaches 0. That's what the derivative means. Evaluate the function at x plus delta x, subtract what it was at x, and divide by delta x. So intuitively what you're saying is integrate this function f of t all the way up to x plus delta x, which is this point here. That'll give you a slightly bigger area, then subtract the old area. So this is going to give you the difference between those two areas, which is just the area under that little slit there. And as delta x gets very, very small, that's going to converge on being a rectangle. And what's the area of that rectangle going to be? It's going to be this side length here, which is delta x. So the area of pink is going to equal delta x times the height of the rectangle, which is going to be f of t evaluated at x, so f of x. So what you're going to end up with basically is the delta x's will cancel, and this derivative is going to become f of x. So the function that you're integrating evaluated at f of x, and that's the rigorous proof of that is the first fundamental theorem of calculus. Okay, right, so similarly here, when we differentiate with respect to t, what we're going to get is we're going to get this function here evaluated at this top limit. It's not just going to be evaluated at t, because when you differentiate, what you're effectively doing is now you're putting a constant on there, then you'd have a constant here, etc. And now this x here, this wouldn't be an x anymore, it would be x plus c. So you'd be evaluating you'd have the height of this rectangle would now be f evaluated at x plus c. So similarly, this is going to be this function within the integrand evaluated at t minus x, and the variable we're looking at here is x, not y. So your y is playing no part in this. Y is sitting there like a constant. So the variable is x, so that's playing the role of t. So it's going to be, with this derivative basically here, is just going to become the joint probability density function evaluated at t minus y and y. And then that's it. That's all of this bit here. So let me get a highlighter. All of this bit here is just going to become that. Okay, right. So what we then therefore get is that the probability density function of the random variable x plus y, which often is called the convolution of x and y, is equal to the integral from negative infinity to infinity of the joint probability density function evaluated at t minus y and y dy. Now, that is what is known as the convolution integral, but there's a better form for it. When you see the convolution integral, you won't usually see it like this, because usually what they will assume is that this function was independent, basically, that the two random variables x and y were independent, and therefore that this convolution, that this function here, this joint probability density function, is just equal to the marginal evaluated at little x, which in this case is t minus y, times the other marginal of y evaluated at little y. Okay, so the convolution integral is usually, the way you'll usually see it written is the integral from negative infinity to infinity of f, the marginal probability density function of x evaluated at t minus y, times the marginal probability density function of y evaluated at little y, dy basically, and that will give you the probability density function of this convolution, i.e. x plus y evaluated at little t. Okay, but remember that relies on the two random variables x and y being independent.